So now we're going to do 9-2. This is kind of a tricky problem because we have a lot of mathematics in this problem. So we're given this kind of wire in this U shape, and we're looking to find the centroid and the X and Y directions, okay? Well, based on symmetry here of this thing, we can tell that the centroid is going to lie somewhere along this y-axis here. So we can automatically say x bar is 0, and that says the centroid is going to be somewhere along this y-axis. The y bar is not as easy. So to figure out y bar, we need to use our formula, which is the integral y tilde dl divided by integral of dl. Okay, so what do these terms mean? Well, dl is just a little bit of this length here, and y tilde is the location of that differential element. So let's just take a look. If we were to zoom in really close here, and let's blow that up and see what that would look like. We have a view here, big zoomed in view. And we would have this small differential length here, and that length is dl, right? That's dl. But we're given this in a Cartesian coordinate system, x and y, so it would be helpful if we could put that in terms of x and y. So we have dx here, that's just a small part of x, and dy is the height. Okay, and the location of this center is then y tilde. Y tilde is nothing more than just x squared. Okay, the location of that. All right, so dl squared is equal to dx squared plus dy squared based on the Pythagorean theorem. Okay. I'm going to factor out this dx here and put it outside. And this just seems like we're doing extra work right now, but it comes in handy later. So what we're going to have is 1 plus dy over dx squared. And then I'm going to pull this dx squared outside here. So if we multiply this dx squared back through, we should get the exact same formula as up here. So why did I do that? Well, it comes in handy when we find dl, so I'm going to take the square root of both sides. So we have the square root of 1 plus dy dx squared. And then outside of this radical here, we then have dx squared, but we need to take the square root of that, so that just becomes dx. Now when we plug this back into our equation here, we have this dx out here, so we can integrate along the x-axis. That's why we do that. So let's start plugging this back in and see what we get. All right, so y bar is equal to, on the top, we have y tilde, which we said was x squared, times this dl here, which is the square root of 1 plus dy dx squared, and then dx on the outside. And then on the bottom, we just have the integral of dl, which is 1 plus dy dx squared dx. Okay, so the next question is, what is dy dx? How do we find that value? Well, we're given y is equal to x squared. So if we take the derivative with respect to x, dy dx is 2x. All right, and 2x we can now plug into here, and if we take the square of that, that's 4x. So let's write this equation again. We have x squared, and we have the square root. I'm I'm going to write that to the half power. That's easier than drawing the radical sign. So we dy dx is 2x, and then we square that. That should be 4x squared. And then instead of drawing the radical, I'm going to just put this to that 1/2 power dx. And then underneath here, we have the integral of 1 plus 4x squared, the 1/2. Okay. So what are we integrating from here to here? Well, if we go back to our diagram, we're along the x-axis, we have this dx out there. So we're going from -2 to 2 to integrate this thing. So the limits on each of these integrals are -2 to 2. Okay. And if we perform those integrals on the top, we should get 16.9423. On the bottom, we get 9.2935. And that comes out to 1.82. Okay. So on that, we've already set x bar is in the x bar is 0, so we're along this line, and then we're like 1.82 here. So this is x bar, y bar is equal to 0, 1.82 feet. Okay, so we're somewhere, that's our location of our centroid for this problem, and that is 9.2.